All right, there, guys. The time has come to talk a little similarity shortcut. So here we go. Of course, pause the video, get all this down that you want. I wrote the questions out ahead of time on the left, but please note that I'm going to probably be moving some stuff around. So be cautious if you're going to try to write all the questions ahead of time like me, because I'm not quite sure how much time we're going to, or I'm sorry, how much room we're going to need for the notes. But anyway, let's jump into it. So the subject for today, the thing I want to talk to you guys a little bit more about is similarity shortcuts. So the idea is I have these two objects. I'm not entirely sure they're similar. I can use a full definition, but I don't know if I really have to. So that's really the big question. How do I prove two objects are similar without using a full definition? So maybe the best place to start is to talk about what is the definition of similarity. So hopefully this is getting tedious. I know it is for me to repeat myself a lot, but that's sometimes the way it goes. But the definition of similarity is explicitly that two objects are similar if and only if their corresponding sides are the same ratio and all the corresponding angles are congruent. So let me record that. Um, okay. So let's talk about what that means just a little bit, if we could. So to kind of give you an example of what I'm talking about, let's rock this one in pink. So to give you an example of what I'm talking about, I have this triangle, let's call it ABC, and let's call those side lengths of ABC X, Y, and Z. Uh, and then we have this other object, let's call it triangle DEF, and let's call its side lengths W, V, and T. We have these angles. Let's say we have the angles over here. Okay, so I can actually claim that triangle ABC is similar to triangle DEF if I can prove all the angles are congruent, that are corresponding, and same thing with side lengths. Now, this is not too difficult since we have everything kind of marked out, but certainly we can show angle A is congruent to angle D, same thing with B and E, and angle C and angle F. Now, to prove the side lengths are all in the same ratio, we just have to show that x over w, which is taking the left-hand sides, are in the same ratio as y is to v, and of course z is to t. Now, the problem with this definition is not that it's difficult to do necessarily, especially when you're given a scenario that has, say, numerical values, but the problem actually comes in with this, the fact that you actually have to prove 6 different pieces of information. More to the point, if I kind of examine my past history in geometry, that we actually do have, come on, we actually do have examples, precedents, if you will, not actually needing full definitions. In fact, I can think of 2 really good examples where the full definition was not even needed. So the answer to this question is ultimately yes. With 2 separate examples, one would actually be triangle congruency. So if you kind of recall what we did before, let's say first semester, we can actually prove triangles are congruent without showing all sides that are corresponding and congruent and all angles are corresponding and congruent. We can actually show them by using some shortcuts. Um, side, 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 angle, and of course angle, angle, side were the ones that we were quite sure that worked for congruency. So there is already a precedent in terms of shortcutting the full definition. The second place where I can say, hey, look, this is something we've not used a full definition would be dilations. Okay. If you can show objects have been dilated, is you actually are proving, good Lord, that the objects are similar. Okay, so they kind of amount to the same thing. Now, this is really good news for us because we know we have this full definition we're trying to meet, but we do have examples of where a full definition was actually unnecessary. Um, so we're probably going to be able to find a way to shortcut this information for our purposes. There probably will exist some shortcuts to triangle similarity. Now, to help us understand where I'm going with this becomes a very important question for us. Is there a link between congruency and similarity? Now, the reason why this is important is because if we look at our precedents, examples of shortcutting full definitions in the past, the only real example we had is triangle congruency. Dilations are fine, but dilations are extremely limited. You have to be on a grid for dilations to actually make sense. I got a knock on my door, guys. Sorry about that. But anyway, as I was saying, dilations are fine, but they're limited because they require grid to use well. And although I pulled up some really fancy grid Cornell paper here, you can't count on making a grid just anywhere out there in the world. I mean, think about the project I had you guys do. I made you superimpose a grid, and that caused all sorts of issues. So dilations, although do shortcut similarity, not so great. But congruency, no, they were in business because those four conditions, side, 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 side angle, side angle, side angle, 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 side, those worked in all possible realms. So if we can establish a link between congruency and similarity, well, then it makes sense that we can at least start with those conditions to prove triangles, the full definition of triangle similarity is unnecessary. So let's examine that. Is there a link? Now, again, the answer turns out to be yes. And some people were very clever in kind of vetting this one out. It turns out that if you look at congruency, or two objects that are congruent, they actually are similar anyway. Allow me to explain what I mean. So I'm just going to use squares as an example. So if I have this square, and I'm using the grid paper purposely here, so all the side lengths are 3, and then of course all the angles are 90, and then I compare it to another shape, same dimensions, all the angles are 90, all the side lengths are 3, I can claim that this object is both similar and congruent. Okay? They're congruent by definition, but they're also similar. That's a terrible similar sign. They're similar by, that's even worse, similar by full definition. Okay? And we can prove that, we can examine that by considering this. If I take all the side lengths, the ratios, that reveals that the k factor is 1. And of course, all the angles equal 90 degrees, and therefore are congruent. So it turns out, if I consider two congruent objects, they're also going to be similar. In this case, k factor just being 1. Now, I know that doesn't seem too mind-blowing, but that's a really important step to understanding how these similarity shortcuts work because it gets our foot in the door. So we at least know that these conditions, side, 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 angle, side, angle, 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 side, work for similarity in at least one case. And we're going to use that later. Now, there's something else that's also worth mentioning, and this is just kind of called kind of pop sciencey, but if you examine the congruency sign really carefully, and you consider that this is actually two signs, then you can kind of read this as being equal and similar. In fact, if you kind of look into the etymology of that sign, you're going to find out that's actually why it was chosen, is because it combines the quality of similarity, with the combinations of equal measure. Right? So, if we know that this definition, if we know that this idea of similarity applies to congruency, at least in the k factor equal sense where k factor equals 1. So a natural place to kind of go was to the shortcuts, which will then apply, and how do they apply? Now, this was really the big question of the day. So it turns out the answer has to do a lot with transition. So I'm going to go here just for a moment, and I'm going to kind of sketch this one out. So we're going to do some kind of messy thinking here. Let's get to a new page. Wow. Okay. So if you consider a shape, and you consider this shape, say under the congruency shortcut of side, side, side. Okay, so let's say I have this. I'm going to keep it just really simple, right triangles. Uh, but being side, 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 we don't know that angle, obviously, right? And let's say we have this as a 5, 12, 13 triangle. Okay? So if I use the triangle congruency shortcut of side, 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 meaning that I'm going to have another triangle with the exact same dimensions, we've concluded, at least we concluded last semester, that if I keep my dimensions the exact same, again, side, 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 then these two objects should be congruent. So we've established a congruency here. Okay? Now, we should be careful because, as we just talked about, there is a link between congruency and similar. So in addition to calling these congruent, I can also call these guys similar. That's really light. Hold on, let me use a different color. Okay, so if these are congruent and also similar with k equals 1, okay, either way, I know that the angles have to match up, so I can actually fill in some information about angles. So even though I didn't start with angle information, since side-side enough was to prove congruency, I know the angles have to also be likewise congruent. Okay. So here's where it gets interesting, because now I started with this object. I've now moved to this middle object. And so the natural thing to now propose is, now that I have this object, now that I'm sitting here with this orange in the middle, 5, 12, 13 triangle, what happens if I just pick another k factor? Like, what happens if I now say, well, I wonder what's going to happen when k equals, I don't know, 3, right? Well, certainly, since I have all the information about this triangle and I'm picking a k factor, uh, the resulting triangle, besides being obviously bigger, should be similar because, again, we started with this triangle and then k factor that one up. So all the angles should match because by design, by dilation essentially, I am expanding this object. Okay, so here is the interesting part. We started with a black triangle. We used side, side, side. K factor is equal to 1 to make a similar object here, the one in the middle. Now that I know that they're going to be congruent and all the angles are going to be the same, I can now take that object and blow it up to any size I want, ensuring that these two will always be similar. Okay? Because by design, I started with a known triangle, and then I'm k factoring it up to a new triangle. So this is kind of like any blown up triangle, any scaled triangle. Okay? So now the really interesting question is, can I somehow show that this object must be similar to this object? Well, it turns out they are for a couple different reasons. Now, the most obvious reason is not so much with the angles and the side lengths, but it's actually using a transitive property. Consider this. I'm going to call this triangle 1. Triangle 1 was similar to triangle 2. Okay. At the same time, triangle 2 was similar to triangle 3. Well, by eliminating the shared pieces in the middle, we can conclude that triangle 1 has to be directly similar to triangle 3 by transition. This is called a transitive property or transition. So this kind of thinking, where I take the original triangle using congruency to get to a k equals 1 triangle, and taking that triangle, blowing it up to get any size triangle I want through any dilation, work for side, side, side. So it immediately, this thinking has to work for all other pieces. Um, Whoa, get out of here. Okay. So if it worked for side, 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 well, then certainly it's got to be able to work for side, angle, side. Side, angle, 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 and angle, side, angle. Because in the same way, this was enough to prove congruency, which also proves similarity for k equals 1. And then you can take that and push it to k equals whatever you want, and then using transit property, relate the last triangle to the first one. So it turns out they all actually work. So we can go back and actually record that in notes. Come on, Notability, work with me now. So the answer to this question is ultimately all of them. So all of them work. So side, 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 angle, side, angle, and also angle, angle, side. And the reason they work is ultimately because of the transit property. So to expand on that idea, so like just for an example, and I'll use a different one this time. Let's use side, angle, side as example. If I have this triangle in which an angle, side, angle was known, and I don't know this one or the other angles, if I maintain that information to a new triangle, and I'll recode this one red uh, here, I know that these have to be congruent, but because they're congruent and how I know congruency and similarity are linked, I can actually also claim that these guys are likewise similar with k equals 1 as a factor. Well, now that I know that they're going to be similar with k equals 1, I know all the other angles as a result. Like I know this angle, I know this guy in both. Then I also know that these sides have to be the same. So essentially I get a full information triangle because I use side, angle, side. So if I push that one step farther, and then now I say, well, I designate a new k factor, k equals k in this case. Well, what I'm going to have as a result, of course, is probably going to be a different looking triangle in terms of size, but because I was starting with a known triangle in the middle, the red one, this side length is going to be whatever the previous side one was times k, and this one's going to be times k, and this one times k. Okay, in other words, these are going to be similar, and that's going to be simply by design. Like that's me blowing it up. And again, similarity transforms will guarantee it. So the transitive property comes into play because if triangle 1 is similar to triangle 2, and triangle 2 is similar to triangle 3, triangle 1 has to be similar to triangle 3. And since triangle 3 was blown up from its similar counterpart, that means it applies to all pieces. So this is a really, really good example. This is really good news because they should all work. In fact, they should all work except plus one more, which we should actually make a little note here. And it turns out that angle, angle, angle was also a working one. So now that brings us to this question: if these shortcuts are all accurate, do we really need them all? And it turns out the answer to this question is no, we do not need them all. And here's the reason why. If you consider uh, angle, angle, angle could actually be cut down to just angle, angle. And the reason being is that the third angle theorem, which says, well, if you know two angles in a triangle, you know the third. Um, so if angle, 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 angle can actually cut down to angle, angle, that means that angle, side angle, and angle, angle, side can also be cut down just to angle, angle. For the same reasons, namely because if you look, you already know oh, geez. You already know two of the angles. So angle, angle takes care of all these cases. So really, we're left with just three needed ones. Angle, angle, because it takes care of angle, 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 side, angle, and angle, angle, side, 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 and side angle side, which is, again, great news because only 3 are needed. All right, guys, that does it for me. Those are the notes I'm going to offer. Some formalization we talked about in class. Again, I hope this helped. Please give you some very formal ways to kind of process information. As always, don't forget to include a summary if you want to score a couple extra points in class. And just as a reminder, hopefully this is getting tedious, the way you're going to do this particular summary is to go back and highlight 3 to 5 words or phrases that you think are necessary to answer the essential question. Craft a summary with those 3 to 5 highlighted phrases, and then post that to Edmodo as a response to this video, and you'll score some extra points. All right. So again, I hope that helped. If you have questions, let me know. We're going to continue this journey of similarity